Welcome back to The Explainer. I am genuinely so pumped to share this one with you today. We're taking a deep dive into the hidden structure of math guided by a truly fascinating paper by Chang-Chai Chen called Recursive Geometry and the Emergent Approximations of Mathematical Constants. Look, if you've ever felt like math was just this chaotic bunch of disconnected rules, this explainer is going to completely change how you view the numbers that make up our reality.
So let's start with a mystery. Think about pi, right? The constant that defines the geometry of circles. Or e, the base of exponential growth. Or phi, the golden ratio, which you see everywhere from proportional scaling to the spirals of a pine cone. For centuries, these constants have popped up in totally different mathematical contexts, and we've basically treated them as completely separate, almost random features of the universe. But what if they aren't isolated at all? What if the constants of circles, growth, and nature are actually born from the exact same underlying equation?
To wrap our heads around how this unified code works, it helps to think of math a bit like DNA. Consider discrete mathematics. You know, your basic 1, 2, 3, simple linear counting. Now, contrast that with continuous geometry. Things like the square root of 1, 2, and 3 drawn from continuous geometric shapes. Historically, we've treated these like two totally isolated strands of mathematical DNA. But today, we are going to splice them together.
Okay, let's dive in. The paper basically lays out an evolutionary ladder for us to climb to see how simple numbers build up into the universe's most complex constants. We're going to hit three main steps: external interaction, internal recursion, and cross-interaction.
Starting right at the bottom rung with System 1, which is external interaction. It's super simple. All we are doing here is taking that continuous geometric curvature, those square roots we just talked about, and adding linear growth to it. We literally just take the square root of n and add the number 1. It's the simplest possible bridge you could build to test what happens when basic counting interacts with continuous geometry.
And the results are kind of mind-blowing right out of the gate. Even with this incredibly basic setup where there's no feedback loop or memory at all, famous constants miraculously begin to surface out of thin air. Plug into 2 and we get an approximation of the silver ratio. Plug into 3 and we get an approximation of Euler's number E. When n is 5, we hit exactly twice the golden ratio. It's totally wild that simply adding 1 to a root sequence starts pulling out these fundamental universal constants.
Now, what's really interesting is when we level up our mathematical DNA. Enter System 2, the Fibonacci Pythagorean sequence. Think of the classic Fibonacci sequence you learn in school, where you add the last two numbers together. Well, here we swap out that simple addition for a geometric combination based on right-angled triangles. It essentially acts as an optimal algorithm for geometrically growing right-angled shapes.
By doing this, we're introducing internal recursion. In plain English, we are giving the math a memory. Every new term now relies on the history of the two past terms, meaning the sequence literally accumulates historical information as it grows. Because of this geometric accumulation, purely additive logic suddenly forces higher-order constants to emerge. We start seeing values matching the silver ratio, different powers of the golden ratio, and, incredibly, approximations of pi.
Moving to the third step of our evolutionary ladder, we get cross-interaction. This is where things get really fun, because we literally cross-breed these recursive systems together. We are splicing the mathematical DNA of the classic arithmetic Fibonacci sequence right into the geometric Fibonacci Pythagorean sequence we just talked about.
When you smash those discrete and continuous elements together within this framework, the output is staggering. This sequence generates values with these incredibly striking, highly structured patterns. Specifically, the constants start popping out in geometric groupings of 3. We're talking e cubed, pi cubed, and the silver ratio cubed. It completely proves that combining recursion and memory drastically enhances the underlying structure of the math.
Now, let me pause for a second, because here is the real so what of the situation. As absolutely phenomenal as it is that we can generate pi, e, and phi this way, the paper does point out a critical limitation. These first three systems are a bit limited in scope. They reproduce a small subset of constants through very specific, almost ad hoc pairings. It is a fantastic start, but it doesn't quite give us the master key to the entire mathematical universe. Which leads us to a massive, thrilling question. To move from these isolated islands of tricks into a truly unified, self-organizing mathematical universe, what if we didn't have to mash up different numerical types at all? What if we could completely replace discrete integers and general irrational numbers, and just build the whole shebang from a single foundational element?
So,
The crucial point here is System 4. This is the absolute climax of the paper's findings. We drop the general square roots, we drop the integers entirely, and we elevate one single element to form the ultimate foundation of the power spectrum. And that golden master key is literally the golden ratio, phi.
Elevating phi gives us the Fibonacci Pythagorean Kepler, or FPK sequence, and the formula is beautifully, elegantly compact. It's driven entirely by raising the golden ratio to half-integer powers. What this creates is a two-sided geometric progression. Because n ranges over all integers, this progression stretches infinitely in the positive direction with exponential growth and infinitely in the negative direction with reciprocal decay.
And this brilliantly illustrates the sheer horsepower of Chung's framework. When we evaluate this single phi-driven sequence, we aren't just finding a handful of constants anymore. We achieve a jaw-dropping greater than 98% match rate in generating over 40 different known mathematical constants.
Let me walk you through this massive aha moment, because it's pretty overwhelming in the best way. Purely by scaling powers of phi, we get the copper ratio from phi cubed. We get the limnescape constant from phi squared. But when we scale the negative powers, it gets even crazier. To put it in perspective, 100 times phi to the negative 11.5 yields Euler's E. 1,000 times phi to the negative 12 produces Archimedes' pi. The sheer volume of famous constants born directly from phi is visually and conceptually breathtaking.
They call this elegant, unified structure the phi ladder, and it completely solves our original problem. When you climb up the positive powers of the ladder, they map out and closely mimic Fibonacci whole integer sequences. But when you climb down into the negative powers, they cascade perfectly into the famous irrational constants of our universe. It is the ultimate unification of discrete and continuous mathematics under one cohesive framework. To wrap up this huge paradigm shift in how we understand numbers, I want to read you a quote right from the source material. Phi serves as the unifying element, capturing aspects of these different domains and enabling transitions between them. This completely reinforces the idea that math is not just a chaotic bag of random constants. It's deeply connected, incredibly structured, and beautifully self-organizing around the golden ratio.
So, I'm going to leave you with this final, mind-bending thought to chew on. If this vast spectrum of mathematical constants, from the geometry of perfect circles to the very rate of exponential growth, all stem from this single, elegant geometric scaling of phi, what other hidden codes are out there governing our universe? Keep exploring, keep questioning, and thank you so much for joining me for this explainer.